All right. Hi, everyone. Welcome to section 7.1. And in section 7.1 and in chapter 7, we're going to be learning about the Laplace transform. Okay. So in this section, it's a bit of an introduction to the Laplace transform. And what we're going to do is define and apply the Laplace transform to functions that we know. Okay, so before we get started with some examples, what I want to do is kind of introduce the Laplace transform, the definition of it, and some relationships. Okay, so throughout your calculus, you have learned that there are different ways to transform a function, one of them being differentiation, taking a derivative, and the other being integration. And these two examples are what's called transforms. This means that these operations, derivative and integration, transform a function into another function. So let's look at a regular example, polynomial example x squared. We've transformed this function countless times. We've transformed this quadratic function into a linear function and a cubic function through differentiation and integration respectively. So, if we take the derivative of x squared, we end up with a linear function 2x. So, quadratic transforms into linear. Well, same thing with the integration, right? If I have x squared, this is quadratic. And if I integrate this quadratic, I get a cubic function. So subconsciously, we've been transforming functions this whole entire time. Okay, and a neat property that these transformations have built within them, you learn these when you learn like the properties of differentiation or integration, is that they have a very satisfying and neat property called linear property. And what that means is that the transform of a linear combination of these functions is also a linear combination. So let's look at these two examples. So right here is the derivative. Okay, and here's the integration. Okay, so if we take a derivative of, two functions, alpha, beta are constants, there's some alpha times f of x plus beta times g of x. Well, they have a linear property that the derivative would be just their sum as well. And same thing with integration. If we're integrating those terms and they're adding up to each other, we can take out the constant and integrate them separately. Okay, so that's the idea. The linear property, it could transform into a linear combination. So that stays through the transformation. So we looked at two types of transformations, differentiation, integration. So in this section and in this chapter, we're going to examine a new type of transformation. It is an integral transformation, although a little different, but that's going to be the Laplace transform. Okay, so in addition to possessing this linear property that we were just discussing, the Laplace transform has many other interesting properties that make it useful in solving initial value problems. So IVPs, we're going to take a look at those later on um, in this chapter. So they help us figure out some initial value problems, meaning like, what does that mean? Solving differential equations. Okay. So it's another way to solve a differential equation, essentially. We've looked at various methods throughout this semester and course. We're going to learn this new method using Laplace transform. So let's go ahead and define what exactly the Laplace transform is. Okay, so the definition, let f be a function defined for values t greater than or equal to 0. The Laplace transform is this setup right here. This L, this is a L. This just means, Laplace. Squiggly brackets, for notation purposes of the specific function f of t, well, the Laplace transform is going to be the integral from 0 to infinity, e to the negative st times that original function that we're transforming f of t. So that's what the Laplace transform is. It's an integral we are calculating, okay? So this is said to be the Laplace transform of a function f, provided that the interval converges. So we need to make sure it converges as well. So this portion here, e to the s negative st, what this is called is the kernel, okay? And then f of t is just our, function we are transforming. Okay. And just some advice with this Laplace transform is that, I'll say like, be careful that, this is an S is the letter and not the number five. Okay. Just be careful with that. Just make sure you know it's an S when you're solving these and not like e to the negative st, not e to negative 5t. Okay, so just be careful. I made that mistake once on a final exam and it messed up my question. So yeah, just be careful with that, okay? Some advice. It's easy to get that mixed up. So one thing you could do is write it like, e to the negative, maybe put some like stop markers around s to make sure it's like s. Um, maybe something that gives you some verification that you're not getting them mixed up, but just be careful. Okay, so just a little background about the Laplace transform is that, the Laplace transform is from the famous French mathematician and astronomer Pierre-Simon Marquis de Laplace. Okay, that's where the Laplace transform comes from. And then what exactly comes out of the Laplace transform is a new variable or is a function in a new variable, f of s. So we're going from t to variable s through this Laplace transform. So let's look at some common examples. Like if we Laplace the function f of t, we get f of s. If we Laplace the function g of t, we get g of s. Same thing, if Laplace y of t, we get y of s. Okay, so some other couple facts about the Laplace transform is that it's defined for a special function that meet these specific two conditions. So the functions must be of exponential order. What does that exactly mean? Well, what that means is that, you know, what does this mean? Well, here it is in English, all right? That the function grows slower than exponential functions. Okay, that's really what it means, that it grows slower than exponential functions, like e to the x. Um, and that if it doesn't converge, then the function is not special. So this limit right here, well, that's exactly what the Laplace transform is. 0 to infinity, e to the negative st, f of t, dt. So if this doesn't converge, meaning our solution does not converge, then it's not special. Okay, one other necessary requirement too is that the functions are piecewise continuous. All right, so no vertical asymptotes essentially from 0 to infinity on t. But okay, so that's kind of our setup. We got our definition. We got a couple definitions for, excuse me, conditions, and then just the overall setup. So in the next couple of videos, we're going to try some make different examples of Laplace transforms of well-known functions. But that's it for the introduction, and I'll see you in the next video. All right, take care.